Hi everyone, welcome to this webinar on Accelerating AI at the Edge with Intel OpenVINO Toolkit. My name is Janakiram MSV. I'm an Intel software innovator, Google developer expert, and a Microsoft MVP on cloud and IoT technologies. I'm pretty excited to bring you this session where I'm going to walk you through the steps involved in optimizing ML models and deep learning models that run at the edge through Intel OpenVINO Toolkit. So if you're attending this webinar for the first time, let me set the context by sharing what is MI2. So MI2 stands for Machine Intelligence and Modern Infrastructure. This webinar series is a platform to explore cutting-edge technologies and emerging technologies. Every webinar that I deliver under this forum is complemented by a tutorial, code snippets, and also a recording of the video. MI2 strives to be an independent and neutral platform for exploring emerging technologies. This is not affiliated to one brand, one vendor, or one platform. Every alternate week, I cover one session from the infrastructure track, primarily focused on Kubernetes, Service Mesh, Prometheus, and related technologies, and also on machine intelligence that covers IoT, edge computing, cognitive computing, and so on. So let's get started by looking at the agenda. But before that, let me bring up a quick poll to make sure that you're able to follow this webinar. So I hope you're able to listen to my voice and also see the screen. So let me know by clicking one of the buttons. Okay, I appreciate if everyone participates in this poll. All right, looks like most of you are able to follow this. All right, so let me close the poll and get back to the session. So I'm going to quickly touch upon the life cycle of a machine learning model. This is how a machine learning goes through training till inferencing. I'm going to talk to you about that. And then I'm going to talk to you about the need to accelerate ML model inferencing, particularly at the edge. And then I'll provide you an overview of Intel OpenVINO Toolkit, followed by an exploration of concepts, and finally a demo that shows you how OpenCV is used with OpenVINO. So this session does expect some understanding of machine learning and some basic experience with OpenCV, but even if you are not very familiar with those technologies, don't worry, you will still find this useful and you'll have all the background required to understand the concept. So let me get started with the life cycle of an ML model. So typically, when you start using a machine learning model, there are two broad phases. The first one is all about training, where we take a historical data set, split that into a training data set and a test data set, pass it through an algorithm or a deep neural network architecture. Okay, looks like there has been an issue. My apologies. So this was about MI2. Looks like I have a different monitor setup and a wrong monitor has been chosen to share the screen. My apologies. So this is what I talked about as MI2, and this was the agenda slide. You haven't missed much in case you're unable to see the screen. So this is the life cycle of an ML model. We have a historical data set that is split into a training data set and a test data set, which is passed through an algorithm or a deep neural network architecture. And it constantly evaluates the outcome of this process by comparing it with the test data set till the results are accurate and precise. And once the model has been trained fully, where the accuracy is meeting the expectations, it is moved to production. It is basically deployed in a live environment where production data is sent to the model and predictions come out of it. So what you see here, where the production data is sent to the model and predictions show up, is called inferencing. So this is the second phase of a machine learning model, whereas till this part where we are evaluating, it is the training part of machine learning lifecycle. Now, even though training typically takes place in the public cloud or in a powerful data center environment, in inferencing, we don't have the luxury of running it on powerful machines or CPUs and GPUs. So these models that are trained in the public cloud are going to be deployed in highly constrained edge environments that may run in very remote locations where power could be a constraint, and even CPU and higher end compute infrastructure could be a constraint. So we need to make sure that the models that are being deployed at the edge for inferencing are fully optimized. So that is what the session is all about. So let me talk to you about the goals for training and inferencing. So training and inferencing, both of them are compute intensive. For that reason, when we are actually using a public cloud platform like Amazon EC2 or SageMaker or GCP AI platform or GCE or Azure ML, we always use a cluster that is powered by GPUs. And those GPUs are going to accelerate training by enabling massive parallelization, and all the mathematical compute intensive operations are typically delegated to GPUs. And that's how GPUs dramatically accelerate the training process when compared to training them on plain CPUs. So the goal for training is high throughput. We want to make sure that massive data sets are going through deep neural network architectures in a highly parallelized form, and we should arrive at results that is basically fully trained model in the shortest possible timeline. So these GPUs and CPUs should deliver highest throughput to basically accelerate the training. Now, when it comes to inference, which are basically models run at edge environments in a constrained environment, the goal there is reduced latency and higher precision, than higher accuracy than precision. So what I mean by that is, it is okay to basically get less precision, but we need to have more accurate results. So we do that by optimizing the neural network models that are typically trained in the cloud, and optimizing it, that is basically by converting the data types, by dropping off some layers in the deep neural networks, and deploying them on specialized purpose-built edge environments powered by highly customized, highly optimized processors and chips that understand how to accelerate AI models. So the inference goal here is reduce latency. So if you remove the hardware-based AI acceleration and run these models on plain CPUs, maybe devices like Raspberry Pi or a BeagleBone or even an Intel Atom, you may not actually get the results that you are looking for. So that's the reason why these edge environments are typically complemented by hardware accelerators that come from NVIDIA in the form of Jetson Nano and Jetson TX2. It could be Intel in the form of Myriad and Movidius. It could be Google's Edge TPU and one of those. So that's what I talk about the inferencing at edge. These are the choices you have. So they complement CPUs with purpose-built chips and co-processors, and they reduce the latency by accelerating the inference. So these compute intensive tasks are typically offloaded to the purpose-built chips. As I mentioned, Jetson TX2 is a pretty powerful inferencing environment, and so is NVIDIA Xavier. And the more recent addition to that family is NVIDIA Jetson Nano. Intel already has a chip that is called Myriad, and it is called VPU because it's a vision processing unit that is optimized for accelerating computer vision models. And then Google got into the game by launching Google Edge TPU. So these are some of the hardware accelerators that are attached to edge devices to primarily accelerate AI inferencing. Now, today I'm going to focus more on Myriad and how Intel OpenVINO as a software layer accelerates AI models. So what exactly is Intel OpenVINO Toolkit? Well, OpenVINO stands for Open Visual Inference and Neural Network Optimization. As the name suggests, it is basically meant for optimizing and accelerating neural networks meant for visual inferencing, which is essentially convolutional neural networks that target computer vision problems. So it enables deep learning inferencing at the edge. So it is a software platform that can talk to a variety of underlying hardware, from a basic x86 CPU to discrete GPU, which is coming from, I need to fix a quick typo, give me a second. There we go. So it supports heterogeneous environments in the form of x86 CPU, discrete graphics cards in the form of a GPU, Intel Movidius neural compute stick, NCS, which I've covered in the previous sessions, and FPGA, which is a field programmable gate array. If you notice, all of them are very different, and they have very different software approach to perform acceleration. The goal of OpenVINO is to provide a common API that abstracts all the underlying hardware environments all the way from a CPU to an FPGA. More on that later. So OpenVINO Toolkit essentially speeds up time to market by exposing functions and pre-optimized kernels that will accelerate inferencing of CNN models. It includes optimized calls for OpenCV and OpenVX. So OpenCV is Open Computer Vision, and OpenVX is another third-party environment, again meant for processing vision computing models. And OpenVINO integrates with both. Today, I'm going to talk to you more about OpenCV and how OpenVINO and OpenCV work together to perform acceleration at the edge. So as I mentioned earlier, OpenVINO is visual inference and neural network optimization. It is actually meant for computer vision models, but the more recent editions of OpenVINO start to support even recurrent neural networks and NLP-based models that are even beyond typical CNNs. So how do you visualize OpenVINO Toolkit? As I mentioned earlier, we have a set of hardware accelerators, or even just CPU and GPU, VPU and FPGA devices. And these devices are basically responsible. These devices are responsible for performing computing. CPU is obviously the core of the entire platform. Then we have a discrete GPU, which is nothing but an Intel graphics card. A VPU, a vision processing unit, that comes in the form of a Movidius neural compute stick or a Myriad X VPU that can be plugged into the PCIe slot, or an FPGA, which is something like an Intel Aria, which is a purpose-built processor for accelerating AI, both for training as well as inferencing. So we have these hardware platforms, and on top of that, there is something called as an inference engine. And this inference engine is like the abstraction that comes with appropriate plugins and libraries for each of these environments. For example, developers will get to use the inference engine, but by changing just the target device, they'll be able to move their deep learning models to one of the supported hardware environments. So the inference engine is the common interface for developers to delegate the inference to one of the underlying hardware platforms. So on top of inference engine, we have deep learning toolkit, which comes with a model optimizer. More on that later. So model optimizer basically takes your existing TensorFlow or Caffe models and optimizes it for inferencing, and that is later on passed on to inference engine. Or inference engine is also capable of taking an existing model and doing the conversion on the fly. But we'll discuss more about it when we come to the demo. Then there is a model zoo, which is a pre-trained set of models that are available on GitHub. You can download a lot of models, for example, emotion detection, facial recognition, age, gender, and a lot of very common models are available in the model zoo. And for most of those models, Intel has already gone ahead and optimized those models for OpenVINO Toolkit, which means they've already done quite a bit of optimization that will enable you to load these models directly without performing the conversion or model optimization. So you should check out the model zoo that's available on GitHub, and there are over 24 pre-trained models and fully optimized models available for you. Optionally, there is an OpenCV component that comes with OpenVINO, and this OpenCV is tightly integrated with OpenVINO. So when you run standard OpenCV programs and use DNN library, which is meant for deep neural network delegation, it will go through the inference engine and talks to the underlying hardware. OpenVX, as I mentioned, is another engine that is responsible for inferencing, but that's not the focus of today's talk. So then we have C++ API and Python API that will enable you to talk to the deep learning toolkit, the inference engine, OpenCV, and so on. So this is the big picture of OpenVINO Toolkit and how the building blocks are laid out. Now, when it comes to understanding the workflow on as a software developer, as either an ML engineer or an edge computing engineer, how do you use OpenVINO? Well, there are two steps. The first step is to train, actually three steps, assuming you're also performing the training. So you first train a model, and for that you basically use TensorFlow, Caffe, MXNet, or one of the supported frameworks. So you train a model and you end up getting a fully trained model along with the biases, the weights, and the complete neural network architecture. So in a Caffe environment, it could be the .Caffe model and the proto.txt file. In terms of TensorFlow, it could be a protobuf, it could be a checkpoint file. So irrespective of what you actually use to train the model, you always get some kind of an output, which is a representation of your model. Then you take that model and run it through the model optimizer. And model optimizer is a simple Python script that basically takes the fully trained model from one of the supported frameworks and optimizes it for edge platform. And the output of the model optimization results in platform independent, framework independent artifacts in the form of a .bin file and a .xml file. So this .bin file contains the weights and biases, while the .xml file contains the neural network architecture. So once you generate these two files, then you can load them in the inference engine and then use the inference engine to basically target one of the supported endpoint devices like the CPU, VPU, GPU, and so on, and you delegate the neural network inferencing to one of the supported or the available hardware environments. So the user application, for example, you could be an ISV who is building a face recognition application, or you could be a retail ISV who is building an application to monitor the stock in the aisles of a supermarket. So when you are building such application, you will embed the inference engine, and the inference engine will use the appropriate plugin to talk to the CPU, GPU, or the supported device, and that loads the IR model. So this is how the workflow is laid out when it comes to using OpenVINO Toolkit. So you train a model, run it through the model optimizer, and get a couple of binary artifacts, actually one binary artifact and one XML artifact, and you load them in the inference engine. You define what device you want to use through the plugin, and then embed that inference engine into your application so that you can infuse AI into your modern applications. So that is the workflow. Now let's understand a bit more about model optimizer and the inference engine. So the model optimizer is basically a cross-platform command line tool, which is acting as a channel between the training and deployment environments. So obviously, if you are bringing a fully trained TensorFlow model or a Caffe model and run it on edge without any optimization, you don't get any performance benefit because these models are expected to be run on very high-end CPUs or a combination of CPUs and GPUs. So when you bring them to edge computing environments where CPUs are very constrained and there is not enough memory, obviously your model loading will take time and inferencing will be, the latency will be very high. So obviously they are not really meant to run in constrained environments. And that's the reason why we need to run it through a model optimizer. So the model optimizer acts as the intermediary between a fully trained model and the inference engine. So inference engine cannot load a TensorFlow model, a native TensorFlow model, or a Caffe model, or an MXNet model. It can only load a platform independent artifacts generated by the model optimizer in the form of the XML and bin file. So here we have the model optimizer, which is taking a fully trained model and generating two files that are fully optimized, ready for loading in the inference engine. So what the model optimizer does is it performs static model analysis. So it basically parses your entire model, whether it is TensorFlow, Caffe, or MXNet, and then understands how the model has been designed, or how the nodes and the neural network has been primarily designed. And then it basically drops certain layers that are not required for inferencing, and it will bypass certain layers, and also converts the FP32, the floating point 32, which is very precise, to a more accurate but less precise data type like FP16 or int8. Because as you can imagine, loading a massive array that contains floating point 32 is going to be pretty hard. Particularly, it is going to it's going to be very taxing for your edge computing environment. A massive array with FP32, floating point 32 type of data set is going to be very difficult, when it is deployed at the edge. Now, if you take the same FP32 tensor or a vector or an array, and without losing much of precision, if you convert them into integer 8 or floating point 16, you reduce the size of the vector or the tensor, and you can actually load a much larger data set in a memory constrained environment. That's the second step, what model optimizer does. It basically analyzes the original data type, which is typically FP32, and converts that model to a data type that is more optimized and aligned with your edge environment, which is FP16 or int8. Now, that is the second step. In the first step, as I mentioned, it does a complete analysis of the model and drops certain layers that are not really required for inferencing, and also layers that don't add value to inferencing, particularly in the context of edge. So that is the job of the model optimizer. Take a fully trained model and convert it into a format that the inference engine can understand. Inference engine has no clue whether the original model was trained with TensorFlow or Caffe or MXNet or an Onyx model. It just expects the IR. IR, by the way, stands for intermediate representation, and that is the combination of an XML and a bin file. So I'm going to show you this in the demo, so stay tuned. So once we understand the model optimizer, let's take a look at inference engine. So once the model has been fully optimized through the model optimizer, then we load it with the inference engine. So inference engine is a C++ library. It also has a Python binding and Python API. But essentially what it does is it is an API that can understand the intermediate representation. That is the combination of XML and bin files. So it basically loads the IR, sets the input and output formats, and offloads the model to one of the desired devices. For example, if you are running the inference engine on top of an Intel Movidius neural compute stick, you just need to change the parameter in the inference engine so that it loads an appropriate binary, which is a DLL in the Windows environment, or a .so binary file in the context of Linux or Mac. So it loads appropriate plugin and then offloads the entire network, the inferencing neural network, to the target device. So that is the job of an inference engine. So that is how you basically use OpenVINO in your applications and in your deployment workflow. Train the model, run it through the optimizer, load it to the inference engine, and start performing inferencing by delegating the model to the target environment. So this is how inference engine basically works. So I have double-clicked inference engine, and as you notice, the output generated by model optimizer is loaded by the inference engine through the common API. And then there are multiple plugins. So there is a CLDNN, which is meant for the deep learning neural network, GPU based plugin. Then there is an MKLDNN, which is optimized for CPU. Then there is a Myriad plugin meant for VPU, which is a vision processing unit. And when you're targeting an ARIA 10 FPGA, then you load the FPGA plugin. All of these plugins are just changing one line of code in the inference engine. You can also dynamically figure out if you have any of these environments or hardware devices available to you and appropriately load the plugin responsible for offloading the model to those devices. So that is the beauty of the inference engine. It's platform agnostic. It can talk to any platform from a CPU to GPU to VPU to an FPGA, and it is framework agnostic. It doesn't care whether the model is trained with TensorFlow, MXNet, or Caffe, or Onyx. By the way, more frameworks are going to be added, like PyTorch. But currently, if you are using PyTorch and you want to use inference engine, you can always run it through Onyx, generate an Onyx compatible model, and then use it with Model Optimizer. So this is how you consume inference engine in your applications. And thanks to the plugin model, as Intel adds more and more hardware for inferencing, the plugins will start showing up and you can start taking advantage of those. Now, when it comes to OpenCV, OpenCV is basically a library used by a lot of C++ and Python developers for performing computer vision based inferencing and processing. So OpenCV existed much before OpenVINO Toolkit became available. But the good news is both Intel and the OpenCV community have worked very closely to perform a tight integration of these two toolkits. So the advantage we have with this integration is OpenCV developers can start tapping into OpenVINO without learning any new constraints. For example, they don't need to learn the API provided by Inference Engine. They don't need to understand intricacies of the Inference Engine, the plugin model, and the API provided by OpenVINO. They'll continue to use OpenCV the way they have been using, and they'll use the most recent addition to the platform called a DNN library, which is the deep neural network inference added to OpenCV, which basically makes it easy for you to load a Caffe or a TensorFlow model and delegate OpenCV inferencing to that model to perform object detection or image classification or object segmentation. So they'll anyway use the DNN library, but now the DNN library not only understands Caffe and TensorFlow, but it can natively read the intermediary file generated by Model Optimizer. So the code remains exactly the same, and OpenCV can now take advantage of the OpenVINO backend by passing the intermediary, the XML and bin file to the inference engine, and the inference engine will get the input parameter from OpenCV on what plugin to use, and it does the rest. So it is pretty seamless and a very smooth workflow. That is the second path where you load models in inference engine native format. But if you want, you can also load the original model, that is basically Caffe, TensorFlow, or MXNet model, and then through the code you convert that into the IR format, and then use that IR with OpenCV. So you can always do that programmatically, but the most preferred mechanism is to load models that are already optimized by the model optimizer into the IE, which is inference engine native format. So instead of doing the on-the-fly conversion, you'll basically do it beforehand and generate the IR and then use it with OpenCV. So that is how you basically integrate OpenVINO with OpenCV. But things get much clearer and become very obvious when I actually show you a demo. So let me switch to the demo, and I will walk you through everything that I have discussed so far, and I'm pretty excited to show you this demo. I spent quite a bit of time optimizing it, but due to the webinar constraints, I cannot show you the entire demo, which is an AIoT demo where I include a couple of IoT devices and perform inferencing at the edge and control some IoT devices, but that's very hard to show in a webinar. Maybe I'll record it separately and upload it to my YouTube channel. But for now, I want to walk you through the code that basically demonstrates how OpenCV is integrated with OpenVINO. So let me switch to the demo. All right, so here we are in my console, where you can see my window. So give me a second, there is something wrong with my window. Let me, okay. So the first step that we're going to do is to optimize the model. And for that, I'm going to run a simple command that's a part of the OpenVINO Toolkit. By the way, you can install OpenVINO Toolkit by downloading the DMG if you are running it on Mac, or it's a shell script if you're running it on Linux. It's an exe if you're running it on Windows. You can download the binary from Intel's website, and you can basically set up OpenVINO. It just takes about 10 minutes for you to set up OpenVINO on your target environment. It also supports Raspberry Pi. Not sure if the Raspberry Pi 4 has been updated, but I have used it with Raspberry Pi 3B+, the previous model. So once you set up OpenVINO Toolkit on your machine, you get this directory called Model Optimizer. So let me switch to that and show you. So once you set up OpenVINO on your machine, you get /opt. Within that, there is an Intel directory, and within Intel, you have OpenVINO. So once you get into OpenVINO, you have deployment tools, and within deployment tools, you find Model Optimizer. And Model Optimizer basically has an optimizer for each of the supported frameworks. For example, if you have a fully trained TensorFlow model, you will run Model Optimizer tf.py. Otherwise, for Caffe, for Caldi, for MXNet, for Onyx, and so on. But there's also a generic one, which is mo.py or Model Optimizer.py, which is the Python file. So we can also use that. But since we are going to use a Caffe model for conversion, we are going to run the Model Optimizer for Caffe. So I have already downloaded one of the popular Caffe models called the MobileNet SSD V1. So in my demo directory, you will notice that I have the Caffe model already downloaded. So this is the typical Caffe model that comes with a proto.txt file and the MobileNet SSD. So let me go to the directory called fp16, and I'm going to get rid of all the files, and I'm going to put this in a watch mode. So I'm going to run watch ls-la. So now, this directory is empty. We don't have any files in this. My goal is to take the MobileNet SSD and convert that into the IR, which is the intermediary representation that is understood by the OpenVINO inference engine. And I'm actually saying that, take this model and turn that into an IR and use fp16. So let me go ahead and run this command. So when I run this, what it basically does is it takes my current MobileNet SSD, passes it through the model optimizer, and puts the output in a directory called fp16, which we are watching here. So when I run this command, it will take a few seconds, and the output is going to be two files. One is the XML file that contains the complete neural network architecture, and the other one is the bin file that has the binary weights. So there we go. Now the output, forget about mapping, that's not really required. It is not a part of the IR expectation. So this is the bin file and this is the XML file. Now, had I converted the MobileNet SSD trained in TensorFlow, I would have anyways generated exactly the same set of files. So it doesn't really matter whether the input is Caffe or TensorFlow. You always end up getting the bin file and the XML file. Perfect. So now we have gone through the first step in the workflow where we have converted the Caffe model into an intermediary. And now what I'm going to do is I will run this at the edge. Now for this demo, the edge is actually my MacBook Air. I'm not using a GPU or FPGA or VPU because the goal here is not to show you the hardware intricacies, but to walk you through the workflow. So now what I've done is inside this directory called model, I have the original Caffe model as well as the bin file and XML file generated by the model optimizer. So now we're going to run a simple OpenVINO program that will perform inferencing. So let me first show you what it takes to write an OpenCV program that natively deals with Caffe. So here is the code, right? So it basically takes the USB webcam, reads from the webcam, and then passes it to the MobileNet SSD. So here, if you notice, this line does the magic. So here we are saying CV2 DNN read neural network from Caffe, and I'm passing the proto.txt and the model file that we have defined here. And what this basically does is it takes this frame that is coming from the camera, and then does a forward propagation for inferencing by passing it to the Caffe model that we have loaded here. And from that detection, which is basically what is coming out from the inferencing, we perform detections and we do bounding boxes and so on. Now, rest of the code is pretty straightforward. It is how OpenCV is written. Now, let me go ahead and run this demo, and that will make things much easier. So now I'm going to launch Infer with Caffe, which is the standard OpenCV DNN program that will use standard Caffe. So let me wait for, there we go. So now on my screen, you see two things, right? One is you can see my face, hopefully. This is actually performing an inference with my camera. So let me increase this a little bit. So here, it is identifying chair and person. Now I'm going to flash a car, and hopefully it also shows up. It also tells you that it is a car. So now you can notice that on my screen, on the terminal, it is printing car along with person. So it is performing inferencing pretty well, and it is using the Caffe MobileNet SSD for performing this. I'm also going to show another object. At this time, it is a bus. And yeah, there we go. It is now detecting bus more accurately. Perfect. And you notice that the frame rate we are getting is not great. That's because we haven't optimized, we haven't done much, and this is running on not so powerful. It's a MacBook Air, much better than any other edge environment, but definitely not meant for inferencing. So now our goal is to use exactly the same program, but with IR. So let me quit this to save some CPU cycles. My MacBook Air is heating up already, and I don't want this demo to crash. So I'm going to quit the OpenCV program. And now what we'll do is I will load the other program that uses OpenCV. So Infer with IR. So now this actually becomes pretty interesting. So I'm going to do a split screen. Okay, so on the top, we have the Caffe model based OpenCV. And here we have the IR based OpenCV program. So nothing changes, exactly the same number of lines. But if you look at line number 10 and 11, Here, I choose to load deploy.xml and deploy.bin instead of proto.txt and cafe model. So that is the fundamental difference, and it is coming from FP16 directory, where we actually stored the optimized IR files that came out of the model optimizer. And the other line that I'm going to change when I'm moving from typical cafe to IR is this line. Here we are actually telling OpenCV to use cafe. So we are using this specific method of DNN library that says read network from cafe. But when it comes to OpenVINO, we are actually saying that read net. We are not saying read net cafe or TensorFlow or MXNet. Instead, we are saying read network generic, and proto.txt and model are no more cafe specific, but they are what we optimize it through the model optimizer, which are nothing but a combination of IR files, which is nothing but a combination of XML and bin file. And then we also tell OpenCV set the preferable target to CPU. Now this is where it becomes pretty interesting. If I have a discrete GPU, I can turn this to GPU. Now assuming I'm running this on Linux and I have a Myriad Movidius stick, I can turn this to Myriad. And if I'm using multiple Myriads, not just one, and I'm using a cluster of Myriad VPUs, I can also target what is called HDDL, which is high density deep learning toolkit. It is going to parallelize my inferencing not just on one VPU but a set of VPUs. So all I got to do is, depending on my current hardware environment, I need to change this parameter, and this is where all the magic happens. So this line, these two lines will tell OpenCV to start using OpenVINO. So when it encounters this line, it knows that it is going to use OpenVINO. And when it comes to this line, it knows that OpenVINO has to talk to the target device mentioned in this variable. So DNN target CPU will target the CPU, but I can go ahead and change this to GPU and or FPGA, and it just works. So now let's go ahead and run this program. Nothing changes. Those are the only minor changes I need to do when moving from native cafe to OpenVINO IR. All right. So now what I'm going to do is launch Infer with IR, and this is OpenVINO specific code. So when this comes up, hopefully we'll be able to see some better performance of the frame rate. May or may not be. The reason being, we are still targeting CPU. We don't have an AI accelerator here like a Myriad or anything. And when I flash an object, it hopefully detects, and it does. So now it actually shows bus. It shows car when I flash the car object, a toy car in front of it, and there we go. It is. I need to calibrate this further, but yes, it does work. I can see occasional car label showing up. So this works. The inferencing is working, and I can notice a slight improvement in my frames per second. Mind you, we are not using any hardware accelerator. Technically, running Cafe directly or IR on the same CPU doesn't make much difference. That's the reason why you don't see a huge improvement in the frames per second. But based on my experience, when I actually ran a very similar experiment on a Raspberry Pi without a Myriad VPU attached to it versus a Myriad VPU, I got about 8 FPS without Myriad VPU, and with Myriad VPU, I have gone up to 15 FPS, which is pretty good. It's performing better than my MacBook Air. So that is the basic workflow, where you take an existing model and you convert it to I think now things will start to make sense, and this is exactly what we have done here. So we have taken original model, ran it through the model optimizer, which is mvo_cafe.py, generated the IR, loaded that IR through OpenCV, and informed to use CPU as the backend, and we loaded a frame from the camera, and OpenCV started to show us the bounding boxes that came via the inferencing engine output. Perfect. So that was exactly what we have done. So that basically brings us to the end of this session, and this was a quick walkthrough of the building blocks of OpenVINO and how to use that with OpenCV. So let me summarize. OpenVINO accelerates AI at the edge. It can run on CPU, it can run on GPU, it can run on VPU, it can run on FPGA. But you don't need to change your code except one parameter. Model Optimizer generates the IR file from an input neural network trained in TensorFlow or Caffe or MXNet or Onyx. And Inference Engine loads the IR files generated by the Model Optimizer and offloads them to the target device that is mentioned as a part of the plugin macro. And inferencing takes place with the help of the hardware accelerator. And thanks to OpenCV integration, you don't need to learn the native API of OpenVINO. If you're familiar with OpenCV, you can continue to use OpenCV, but delegate inferencing to the inference engine of OpenVINO Toolkit just by changing a couple of lines of code. Actually, I want to show you something before we conclude this session. So let's say I launch Python 3 environment and I import CV2, which is the OpenCV environment. And when we actually print the CV2 version, you'll notice that, okay, CV2 dot, okay, you'll notice that this is OpenCV 4.1.2, but it also has a suffix of OpenVINO. And what this means is the OpenCV version that I'm running on my machine came bundled with OpenVINO, and it is highly optimized for OpenVINO. That means OpenCV is aware of OpenVINO's capabilities and it can talk to the inference engine. So this was what I actually wanted to show right at the beginning, but somehow I missed. It's not too late. So hopefully this makes it clear on how OpenCV and OpenVINO work together. Basically, Intel has bundled a version of OpenCV, highly optimized for OpenVINO along with the toolkit. So that's what I meant by the last point. All right, so that brings us to the end of this session. It was a quick introduction and walkthrough of OpenVINO. I want to thank our sponsors, Google Cloud, for supporting me with all the background credits and validating my content. NewStack, my media partner. Last week, I already published an article on overview of OpenVINO, how OpenVINO makes it ubiquitous to run AI models at the desktop and edge. This week, tomorrow evening, you'll actually find an article that goes live at the NewStack, which has the complete tutorial that I have shown you today in this webinar. So if you're watching this on YouTube, look at the description. There should be a link to the tutorial and the concept that I have published. So thanks to NewStack for being my media partner and publishing relevant content that aligns with my MI2 webinars. Foghorn, an edge computing company based in Bay Area that targets multi-cloud environments. Portworx, a cloud-native storage company that makes it easy to run stateful workloads on Kubernetes. So at this point, I want to bring up a quick poll and get your feedback. So how relevant was the webinar content? Did you get what you expect? So when you signed up for this session, you would have some expectations. Did it really meet all those expectations? And was this relevant for you? Fantastic. 100% of you said it is very relevant. And some of you are now saying it is somewhat relevant, but I'm glad that most of you or all of you found this relevant. Excellent. And finally, how do you rate the overall quality of this webinar? This includes everything from the content that I have prepared, the visuals, the quality of demo, my presentation, everything. All right. Thank you. Again, most of you felt it is excellent and some of you felt it is good. It's very encouraging. I'm committed to bring you high quality content on emerging technologies through MI2. Thanks again for your feedback. And now it's time for me to announce my upcoming session. I'm pretty excited to announce the next webinar on October 24th on everything you want to know about Knative. So Knative is an open source project built by Google, Pivotal, IBM, Red Hat, and others. It's a pretty interesting project that brings in serverless capabilities to Kubernetes. So as a part of my infrastructure track, next week, or I'm sorry, the week after, I'm going to talk to you about Knative. And like most of my sessions, there is going to be a deep dive demo to help you understand what is Knative and how those capabilities bring serverless computing to Kubernetes. So do sign up at mi2.live, and I'm going to see you in my next webinar. Have a good rest of the week, and I will see you soon on 24th. Thanks once again for joining my webinars. If you are finding this useful, please ask your friends to sign up at mi2.live, and do visit the YouTube channel, which I'm going to share through the email that I'm going to send to you. And if you're watching this on YouTube, don't forget to subscribe to my channel. I'm committed to bring you new video every alternate week from the modern infrastructure and machine intelligence tracks. Thank you. Have a great rest of the day.